The fourth presentation in Unit 2, entitled For Every Action, says for every action there's an equal and opposite reaction plus a social media overreaction. So, the learning goals are that you be able to conceptually and mathematically apply Newton's third law of motion, which is referred to as the action-reaction, and integrate all of Newton's laws to describe the motion of an object. So, what we already know. We already know that forces cause the change in the motion of an object. The greater the force results in the greater acceleration, and that multiple forces can be exerted on an object. So, what we learned in the lab, that air has a force that's exerted on it as it accelerates out of the balloon. So, when you release this thing, air is accelerated out of the balloon backwards. So, there's a force exerting the air, pushing it outward. That the balloon in turn accelerates in the opposite direction. And we also know that the acceleration of the balloon is less than that of the air. The air comes out a lot faster than the balloon itself moves. So, we know that pushing off. Whenever you exert a force on a wall, it doesn't necessarily move the wall, but the swimmer accelerates in the opposite direction. There's lots of other situations in which this is true, especially in things like track, whenever you're doing a push-up, or anything in which you're required to exert a force against some sort of surface. Now, it's not that that the surface itself isn't moving, it's the fact that it's attached to a very large building. But we have Newton's third law. Newton's third law says that for every force, there is an equal and opposite reaction force. So in this case, the force is exerted on the wall. Okay, so the force is exerted on the wall, and it does actually accelerate the wall a little bit. The reason why it's not noticeable is because it's attached to a very, very large building. If you were to measure the acceleration of the particular wall after you push off it, it tends to be very, 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 very small. Okay, billions of times less than you can actually detect. Now, the reaction force is the opposite force, and that's exerted on the swimmer. So the force that you exert on the wall is the same as the force that the wall exerts on you. So you end up getting the same force that you exert. So the harder you push on the wall, the more the wall pushes back and causes you to get a bigger jump. But the key thing is that the reaction force and the initial force have the same magnitude. So they're the same number. So the more you push off, the more it pushes back. Now, a lot of times people say, well, wait a second, if that were true, then you'd have this cart and this horse problem. So if you were to, if the horse exerted a force on the cart, okay, and the cart exerted an equal and opposite force on the horse, it would never move anywhere. And that's true to some extent because they're exerting forces on each other backward and forward. But there's a difference in this case and that's the idea of friction. Okay, there is friction in which the hooves of the horse can actually prevent this backward movement, this force from exerting it on the horse. It balances out. Where there is no friction between, or there's very little friction between the wheel and the ground. So as a result, the fact that you have friction allows the horse not to move backwards, but it does instead allow the wagon to move forward. So that's the whole cart before the horse question. Next, we have action-reaction Jedi style. I would highly suggest that you take a look at this link. This is a famous duel between Anakin and Obi-Wan Kenobi in Star Wars Episode 3, Revenge of the Sith. And what you'll see is Jedi action-reaction Jedi style, where they actually exert equal and opposite forces on one another, driving each other backwards. So now, you have Newton's third law of motion, which says this. This is the mathematical version of this. But what it's saying is that if I have a force, if I apply a force of 100 newtons to the right on an object, then it's going to exert an equal and opposite force, equal in magnitude, and opposite in direction. The negative indicates opposite in direction. So this is Newton's third law in just the mathematical terms. So, if it says a rocket is launched upward with a force of 100 newtons, what is the force exerted on the gas escaping the rocket? It has to be equal and opposite. So, if the rocket is moving upward with 100 newtons, then the force of the air has to be downward at 100 newtons. Equal and opposite. Next, it says, what is the action-reaction pair for a high jumper? And this one is kind of interesting because it's a little bit confusing. Whenever you exert a force on the ground, you are the action force. So the action force is the person pushing Earth. The reaction force is the Earth pushing you, which is kind of weird. But that's the reason why when you exert a force on the ground, so you're pushing down, your body moves up. Next it says, which will have the greatest acceleration, a cannonball or a cannon when fired? Now remember, there's going to be an equal and opposite force. So if you exert a 100 Newton force on the cannonball, there's going to be a 100 Newton force on the cannon. Now the reason why the cannonball has a greater acceleration is because you have to remember force equals mass times acceleration. Just because there are equal forces does not mean there's equal change in motion. If you were to look, forces are the same, but the mass of the cannonball is much, much smaller than the mass of the cannon. So although the cannon does move backwards a little bit, it accelerates a little bit, it doesn't accelerate nearly to the degree that the cannonball does based on the fact that they have different masses. And finally, you have a 25 kilogram boy pushes his 100 kilogram dad with a force of 20 newtons on a frozen pond as shown below. What is the acceleration of each? So the first thing you see is that the boy exerts a 20 Newton force on his dad. So you have a 20 Newton force exerted to the left and on this guy. So if we were to look, we can go ahead and find the acceleration of the dad. You have a force of 20 newtons. You have an acceleration, which is what we're trying to solve for, and you have a mass of 100 kilograms. F equals ma, or 20 equals 100 a. Divide both sides by 100. It's just rehashing Newton's second law. You get a equals 0.2 meters per second squared. Now that's for the dad. If you were to look at the boy, remember that there's an equal and opposite. Whenever you push somebody, you have that same force exerted on you in the opposite direction. So this boy, the dad, has an acceleration of 0.2 meters per second to the left. The boy is going to have a 20 Newton force exerted on him. We're going to try and solve for his acceleration, but his mass is much less. It's 25 kilograms. So now whenever we do this, we would say F equals ma, yes, but now the force is going to be 20 newtons, and it's going to be to the right, not to the left. So now we can say 20 equals, and then our mass of the boy is 25, and then a, divide both sides by 25. And when you do that, you get 20 divided by 25 is 0.8 meters per second squared. So you have 0.8 meters per second squared and 0.2 meters per second squared. So the boy will have much greater acceleration due to the fact that he has a lot lower mass. And they do go in opposite directions. So the boy will end up over here, and the man will end up over here on opposite sides of the frozen pond.